Hello everyone, I am Pritam. Recently I am a researcher with the background of material science and chemical engineering. So a few months ago I just finished my PhD with the topic of biomaterials for tissue engineering applications. So today I am going to explain some of the basic principles of tissue engineering and also some of our overviews that I have done during my PhD. So this work was funded by Erasmus Mundus doctorate in membrane engineering, and this work has done in between collaboration of 3 universities. That is University Paul Sabatier in France, University of Calabria in Italy, and University of Twente in Netherlands. Tissue engineering or regenerative medicine, it is an interdisciplinary field which refers to develop functional biological structures or human tissues inside a laboratory with some bunch of cells. The ultimate goal of tissue engineering is to use those functional biological structures and implant inside the humans which were damaged due to diseases or traumatic injury or genetical disorders. Tissue engineering is mainly dependent on 3 very important factors, which are namely the biological science, the material science, and the bioreactor. The biology, it refers to use the right cells to reach the target tissue construct, and also it refers to the right bioactive molecules to keep the cells healthy and productive. The materials or the bioscaffold, it refers to provide the right environment for the cells. Sometimes the materials can dissolve over time inside the human, sometimes it can remains inside the body to support the organs for lifelong. The bioreactors, it refers to provide the essential physical and mechanical forces to influence the cellular development. So why the research and development in tissue engineering is so important in the modern medicinal field? I'll show you how. Tissue engineering has revolutionized the modern medicine in the last 4 decades. In 1980s, it was the first 2 successful attempts was reported for artificial skin reconstructions. From then, nowadays there are extensive research is already have done in the all vital sectors of tissue engineering like liver, cartilage, bone marrow, skin. Here are some examples of tissue engineered construct which are successfully implanted inside the human, like cartilage, bladder, small trachea, or small arteries. So this all happens in the last 40 years. I mean, it is a remarkably very short period of time. Back then in 80s, these kind of things are like completely hype or like a science fiction. In today's world, these are the reality. So this includes many interesting and very efficient technologies. So here I would like to show you some examples, like cell cultures with 3-dimensional cell-filling hydrogels and use it for corneal reconstructions. 3-dimensional bioprinting to develop human organs like bone, ear, nose. Another very important is 3-dimensional scaffold fabrication. The first part of our work was highly influenced by this technology. Here are some examples like liver cell ingrowth or cancer cell entrapment inside 3-dimensional porous polymer scaffold, or vessel repairment by using small diameter polymer conduit. Another example is the organelle chips. It is a recently emerging field and also very efficient as it holds the complexity of the human tissues in a very simplified and very controlled way. So the other part of our work was also highly influenced by this technology. So there is a small video description to explain how it does work. So usually organelle chips, they are consisting of small microfluidic channels which are often interfaced by porous scaffold upon which we can see human cells. By this, it can mimic the bioenvironment of many vital human organs. So that is a very nice examples as a lung on a chip which was reported in Science. Nowadays there are all vital organs are already reported inside an organelle chip device like liver, gut, lungs, heart, bone marrow. Here is another example of eye on a chip. It is an ongoing project which was going on in University of Twente by my fellow researcher. So like this, there are numerous examples are there. All of these things happen in just 40 years. It's a revolution, isn't it? The general principle of tissue engineering. The central idea of tissue engineering can be simply defined by seeding living cells inside a three-dimensional porous scaffold. Although there are many other approaches to do so, but this approach, I would say, it will dominate in this field in the last few years. To develop a tissue construct from some bunch of cells, it will need proper nutrients and conditioning. So let's say we prepare a tissue construct in a day to a month scale. So in between there are number of functions are going on. So let's see. So first of all, the scaffold will degrade over time while the cell will grow. While the cell will grow, they will also increase the mechanical property. It can depend. I mean, if we implant the scaffold seeded with the cells inside a human, so in the beginning it can decrease the mechanical property, but at the end it will again increase in strength. While the cell will grow, they will suffocate for oxygen, and that is how they will prepare the blood vessels by the mechanism called angiogenesis. There will be another function inside the tissue construct. It is called inflammation. So it doesn't matter how much biocompatible the material is, it will always possess some inflammation. But it is a very normal thing. With time it will go away. So at the end we have our tissue construct while the scaffold will be completely gone. Now the scaffold can be implanted inside the human or the animal is mostly by three ways. The first one is where we directly construct the tissues inside a laboratory, and then we implant the tissue construct completely inside a human or in an animal. The second one is also very popular, like when we implant the scaffold while the cell will still growing. This is very important in those cases where you when you do not have so much time, where we have some traumatic injury. The number three is also very popular, like when we when we implant the scaffold without seeding any cells. So most of the time in that cases, the scaffold remains inside the body to support the organs for lifelong. So by this I will finish the overview of the general principle of tissue engineering, and from now on I will be more intent to show you our actual work that we have done during my PhD, some of our overview, some of our good results that we have done. So our work was mainly on cardiovascular system diseases. It has been said that the cardiovascular system diseases like atherosclerosis, they are directly or indirectly responsible for half of the deaths in the modern world each year. So here is an example of a normal blood vessels, which consists of three main things. That is the normal endothelium in the inner luminal side, which is surrounded by smooth muscle cells, and in the adventitial side or the outer layer is the collagenous layer. And here is an example of a damaged blood vessels with a damaged endothelium. So how does it happen? Due to excessive smoking, alcoholism, uncontrolled life, obesity, hypertension, the body starts releasing toxic chemical components inside the vessel, and it will rupture the endothelium, and eventually it also releases cholesterol, which will clog the vessels. So very often the patient has to go for surgical procedure like a coronary bypass surgery, where they has to replace the damaged vessels by autografts, by taking vessels from their own body. So here we intend to regenerate the artificial and the biofunctional vascular graft seeded with cells, which can be replaced inside the body of a human. So two kinds of cells can be seeded as a co-culture. First of all, mesenchymal stem cell, which will go inside a three-dimensional porous scaffold, and later on we will seed endothelial cells in the luminal surface. Using a mesenchymal stem cell has many promising and many beneficial effects, because mesenchymal stem cells are very fast growing cells and they are pluripotent cells. If they can genetically modify it, they can release bioactive molecules or growth factors, which can increase the efficiency or the longevity of the endothelium in vivo system. It can also change their lineage in completely a different cell type depending upon the environment. So it can change the lineage in a smooth muscle cells. So our idea is to use this kind of cell-loaded three-dimensional scaffold and to replace inside the damaged part, while the cell will grow in vivo and the scaffold will be completely gone and it will heal the surface. Okay, so that is the roadmap that we have followed during our PhD. So we intend to prepare a three-dimensional polymeric scaffold in terms of flat sheet membrane, which will consist of double porous morphology. So there will be a bigger holes which are open on the surface, ready to access the cells, as you can see here. And these big holes are connected with a small spongy porous network in order to transfer essential nutrients, growth factors, oxygen inside the bigger holes to keep the cells healthy and productive for a longer time. Our second goal was to seed mesenchymal stem cells in a static cell culture to understand at first the biocompatibility of this kind of morphology, and then also to understand the cell matrix interactions and also the very important the cell invasion phenomena inside the scaffold for a longer time. And our third goal was to mimic the in vivo human physiological condition in a dynamic cell culture by using HUX, which is a human umbilical vein endothelial cells, inside an organ-on-chip device. So here we intend to measure the hydraulic resistance of the cellular layer by using trans-endothelial pressure. So for our material, we choose Polycaprolactone and Chitosan as our basic polymer because both of these two polymers is biocompatible and bioresorbable. They have an excellent ability for cell adhesion, and if you see the other properties like mechanical properties or the degradation properties, those are complementary with each other. So mixing these two kind of polymer will be a very good deal which will eliminate all the negative points of the individual polymers. So we prepare the flat sheet three-dimensional porous scaffold by a liquid-induced phase inversion process. So where we dissolve these two polymers in a common solvent and then we cast it in a glass plate, and then we put this polymer solution inside a non-solvent bath containing sodium hydroxide solution. So that is the way of doing classical phase inversion process. But here we modify the classical phase inversion by using trackaged isoporous membrane. So just before putting inside the non-solvent bath, we apply this trackaged membrane on the custard solution, and then we put inside the non-solvent bath. So due to the presence of this trackaged isoporous membrane, it will trigger a heterogeneous solvent exchange in the interface of the solvent and the non-solvent. So which will at the end result with the double porous morphology like that. So here is a snapshot to explain you how we achieve this double porous morphology. So here is this photo was taken in that place where you can see the double porous morphology where we apply the trackaged membrane, and the single porous morphology where we did not apply the trackaged membrane side by side. This is the top surface and this is the cross section. So that is the utility of using this kind of trackaged isoporous membrane to achieve the double porous morphology. So after formation of the double porous morphology, we at first characterize morphologically. So here is the image of the membrane. It was taken in that place where we did not apply this trackaged membrane. So as you can see, it is forming a single porous closed structure. There is no open holes on the surface, so the cell cannot invade inside the bulk, nothing to work with. So now I'll show you the photos which were taken in that place where we apply the trackaged membrane. So first of all, we prepare 4 batch of samples, that is pure PCl Chitosan with the ratio of 90-10, 80-20 and 70-30. This is the photos on the top surface, this is the photos in the cross sections. And all of them are showing the double porous morphology. As you can see, there is bigger holes which are open on the surface, and also in the cross section you can see the bigger holes are connected with each other by this spongy small porous network. So it is actually fulfilling our first criteria, that is the double porous morphology, where we can do the cell seeding in a 3-dimensional way. So after formation of the double porous membrane, at first we go for the cell seeding to understand the cell matrix interactions, and also the most important, the cell invasion phenomena, to see whether the cell really can go inside the porous morphology or not. So we seed mesenchymal stem cells for longer time, for 21 days. And then we take the photos in a Z stacking mode, that is, we take the photos from the surface towards the bulk every certain micrometer intervals. So here we stain the cells, that is the nucleus by DAPI in a blue color, the cytoskeleton in a green color by vimentin, and the cell surface by CD90 in a red color. So first of all, I show you the photos that was taken on the surface of pure PCl and PCl Chitosan 9010. So here you can see the photos from the surface towards the bulk. We can see the cells are on the surface by taking a cylindrical morphology, but while we are going towards the bulk, there is no cells. So for these two scaffold, there is no cell inversion was happening, because in these two scaffold, the size of the big pores are not big enough that it can hold the cells inside the bulk. We did the same thing for the last two scaffold, that is PCl Chitosan 8020 and 7030. And in that case, we find that the cells are on the surface by taking a higher surface area. And also, when we are going towards the bulk, we can see there is also cells inside the bulk by taking a globular morphology. So it is very important for us, that is telling us that in these two cases, in these two scaffold, the size of the bigger holes are big enough so that the cell can invade inside the scaffold and they can live for a longer time. So it is actually fulfilling our most important criteria. So after having some positive results from the static cell culture with the mesenchymal stem cells, then we move on for dynamic cell culture in an organ-on-chip device by taking HUVEX with endothelial cells. So here is the image of the organ-on-chip device in the inset, that is the real image that we fabricate for our experiment. And here is the 3D image, as you can see. So basically, it is a PDMS organ-on-chip device consisting of two microchannels where we embed our membranes in between the cross channels. So after fabrication of the PDMS device, organ-on-chip device, we flow culture solution by fusion system. So here you can see the setup of the fusion system. So here we flow culture solution from the reservoir to the top channel with physiological trans-endothelial pressure. So when the culture medium will reach to the top channel, as you can see, there is other end of the top channel was blocked by a pipette tip. So the culture medium has to come to the bottom channel by passing through the membrane. So once the culture medium will be in the bottom channel, there is something happening very important. So if we zoom in that place, so you can see that is the top channel, that is the bottom channel, which are interfaced by the membrane. So here is the flow of the culture medium, which is coming in the bottom channel by passing through the membrane. So once the culture medium is in the bottom channel, you can see there is another end of the bottom channel was also blocked by the pipette tip. So now there is only one way left, which is that one. So the culture medium has to come from this way and it will reach to the flow rate sensor, and that flow rate sensor can give us the real-time flow in per time interval, and by this we can easily calculate the flux, the permeability, the resistance, everything. Now if we seed the endothelial cells on the top channel, the cell will grow and they can decrease the flux from the top channel to the bottom channel. And if the endothelial cell make a nice monolayer with a strong cell-cell interactions, they can eventually stop the flux from the top channel to the bottom channel. Now the question is why we did like this. If you really remember our state of the art, so we intend to apply this kind of cell-loaded three-dimensional scaffold inside the damaged vessels, where the vascular scaffold has to stop the fluid flow from the luminal side to the adventitial side by sustaining the trans-endothelial pressure of 2 to 10 kilopascal. So that is the exact mimicking of the physiological human condition. So here our objective is to seed the endothelial cells on the top channels and then measure the flux of the endothelial cells or the resistance of the endothelial cells with time intervals. I have to also say that we just published this work, so you can also find this work in our ResearchGate link or in online. I will put the link in the video description. So after fabrication of the organelle chip device and also seeding the endothelial cells, at first we determine the hydraulic flux of the endothelial cells. So here is the graph of a flux versus different membrane, where the yellow bar is representing the flux of a blank membrane, the blue bar is representing the flux of seeding cells after 1 day, and the green bar is representing the flux of seeding cells after 3 days. We find the results are really interesting, that is, from day 1 to day 3 the flux was really decreasing. There is a significant decrease we find in all the scaffold from increasing from day 1 to day 3. And also by increasing Chitosan concentration, we also find that there is also a significant decrease of the flux. You can see the pure PCl, it is decreasing from minus 27%, whereas in case of PCl Chitosan 70, there is a minus 41% of decrease of flux. So from here we also determine the resistance of only the cellular layer. So we transform this flux value in a resistance by this simple formula, and then we subtract the resistance of only the membranes by the resistance of 1 day and 3 day, and then we end up with these values of the resistance of only the cellular layer. So as you can see here, the resistance was increasing from day 1 to day 3, and very interestingly, you can see by increasing Chitosan concentration, the resistance was significantly increased. That is, in case of pure PCl, it was a 20% increase from day 1 to day 3. Whereas in case of PCl 70-30, the resistance increased up to 200%. It's 10 times increase. So after having that results, we are really positive. So just after the flux experiment, we fix the cells in the intersection point and we imagine in a confocal analysis. So that is the image after day 1. So here we stain the endothelial cells by 3 parameters, that is the nucleus by doping in a blue color, the cytoskeleton by phalloiding in a green color, and the cell surface by V-cadherin in a red color. So we also seed the cells on the PDMS device, which is tell us the cell morphology as a control. We take the photos in a 15x magnification, which are shown in the insect, and also 85x magnification, which are in the broader view. What we find is that in case of PDMS, the cellular morphology was the best, because PDMS is a smooth surface, and in the initial days, cell would like to adhere on a smooth surfaces. In case of our scaffold, we find that by increasing Chitosan concentration, the number of cells are increasing. But in case of V-cadherin staining, we can find that PDMS also showing very nice expression of V-cadherin. Here I also would like to point out that this expression of V-cadherin we can only see if the cell will make a nice cell-cell interactions. If the cell cannot make the interaction, we cannot see this expression, and it is very important, because if the cell will make a strong interactions, then it can eventually decrease the flux. So after day 3, we find the story was a little different. So in this case, we find in case of PDMS, the cellular morphology and the number of cells are not so nice anymore like day 1, because PDMS, maybe it is a smooth surface, but it also a hydrophobic surface. And we did this experiment in a dynamic way, where we have to change the media and there is a continuous flow of culture media. So some of the cells can peel off from the PDMS surfaces, but in our membrane scaffold compared to the PDMS, they are showing significant improvement. For example, the number of cells, they are also increasing very high by increasing Chitosan concentration. As you can see, it's completely make a confluent monolayer. And also, the very interesting is the expression of the V-cadherin. They are also significantly improved, as you can see. So that is the reason why the flux was decreasing from day 1 to day 3, because the cells are making very strong interactions by making a confluent monolayer. So in a conclusion, I can say that we prepare a 3-dimensional porous scaffold consisting of bigger holes connected with a small porous network, and by increasing Chitosan concentration, we find that the size of the bigger holes are increasing, and also the chemical functionality of the scaffold was also increasing. And we find in the static cell culture with mesenchymal stem cells that the cells can invade inside the scaffold and they can live for a longer time. And also in dynamic cell culture, we find that by increasing Chitosan concentration, the endothelial cells, they can able to increase the cellular resistance very high, and also the cell-cell interaction was also very nice. So as a perspective, we can say that we already have some positive results of seeding these two kind of cells, that is the stem cells and also endothelial cells, in this unique double porous morphology. So in future it will be very nice, we can directly construct a three-dimensional hollow fiber membranes with this unique double porous morphology, where we can seed these two kind of cells, and then we can use this kind of biofunctional morphology inside a human as a vascular 3D implants. So with this I finish my topic. So at the end, I really would like to thank all of my supervisors who were involved in this project. So from my first university in University Paul Sabatier in France, my supervisors were Professor Patrice Bachan, Dr. Jean-François Lahit, Professor Jean-Christophe Remigi, Dr. Barbara Garbi-Susini, Dr. Clemens Koester, and Engineer Sandin Disclose. My first collaboration was in University of Calabria in Italy, and my supervisors were Dr. Simona Salerno and Dr. Loredana Di Bartolo. And my second collaboration was in University of Twente in Netherlands, and my supervisors were Dr. Andreas Vandermeer and Professor Rob George Lamartine. And by this, I also would like to thank my funding agency, that is Erasmus Mundus Doctorate in Membrane Engineering. And this video was completely for educational purposes. And I really would like to thank all of you. Tell me how do you like my work, and please give a comment in the comment section and like and share. Thank you very much for your attention. Thank you.